Hi students, welcome to my lectures. We are going ahead for the estimations of volume using pressure and temperature for the liquids as well as vapors. Okay, before we get into this topic, we are making some basics strong to make sure that what kind of phase that we are dealing with. If you are dealing with liquids, then we have to use the certain set of equations to find out the liquid volumes. If you are dealing with the vapors, we are trying to use certain sort of equations and correlations to find out the vapor volumes. Before you do that, you should first of all know whether you are dealing with the liquids or vapors. I have certain small common sense procedure to identify what kind of phase we are dealing with for a particular substance. Okay, and so imagine that we have already discussed about the PT diagram, in where on we have three things. One is a solid phase, liquid phase and vapor phase. We are into the at the border of the liquid and vapor phases. Okay, based on there are certain principles that comes ahead to identify what kind of substance we are dealing with, whether inside the system, whether we have a liquid or a vapor. If you can able to identify what kind of things that can able to contain within this particular system, so we can apply appropriate equations to find out the liquid volumes and vapor volumes. Okay, so why we have drawn this PT diagram? Here you can see this is called the vaporization curve, where liquid to vapor and vapor to liquid transitions we can observe. That means on this particular line, any point, you take this point or this point or this point or this point, this shows the saturation pressures and saturation temperatures. You can see if you draw a horizontal line and vertical line, you are going to get the saturation pressure value here and saturation temperature value here. If you are at the other point, this is the saturation pressure and this is the saturation temperature for any substance, because every substance has got its own kind of PT curve. So using the information about the saturation and saturation pressures, we can able to identify in this particular system whether it is a liquid or a vapor. With what information? With saturation pressures and saturation temperatures informations. Okay, so that is what let us say there is a system consisting of a substance which can be liquid or a vapor, or it can be vapor liquid. The combination of simultaneous existence of vapor and liquid we cannot identify. So let us assume there is a substance that is present. We can able to only identify whether it is a liquid or a vapor. Okay, let us find out. So to do that, what we need the help of the saturation pressure and saturation temperature data, because this saturation temperature and saturation pressure data can able to allow us to identify what kind of substance that can present in the system. So that is why let us take a imagine I have a temperature bath, so inside which a piston and cylinder is kept. So I can able to change the pressure by keeping more blocks on the top of the piston, and I can able to change the temperature by changing the bath of the liquid. So I can able to maintain a system at any particular temperatures and pressures. So let us assume I have saturation pressure and saturation temperature data. Identification of saturation pressure and saturation temperature at vapor liquid equilibrium. So what is the saturation pressure and saturation temperature? That means it is such a temperature and pressure where substance can exist as a able to exist as a liquid as well as a vapor. Okay, either it can completely exist as a liquid at saturation temperature and saturation pressure, or it can completely exist as a vapor at saturation pressure and saturation temperature, or it can exist like a vapor plus liquid at this same condition. That is what the beauty of the saturation pressures and saturation temperatures. So now we are into identification of any one phase, whether it is a liquid phase or a vapor phase. So let us assume presently the system is at the saturation pressure and saturation temperature conditions. What happens if you increase the temperature, and what happens if you increase the pressure, and what are the phases that form if you change the temperatures and pressures? For example, the system which is at the saturation temperature and saturation pressure, if we increase the temperature higher than the saturation temperature at same pressure, only vapor will exist. Example, we are keeping the pressure constant. I am changing the temperature. What happens? At constant pressure, if you increase the temperature higher than the saturation temperature, that means only inside this chamber vapor will exist. Okay. So, second statement. If we decrease the temperature lower than the saturation temperature at same pressure, only liquid phase will exist. Let us assume I have reduced at same pressure, that means at saturation pressure, let us example the system is at Tsat and Psat. I have reduced the T. What happens? If we reduce the temperature less than the saturation temperature, so the thing's entire system will be in the liquid phase. So that is what this is, the entire picture that talks about the identification of phase, okay, whether it's a liquid phase or a vapor phase. So in summary, that if P is, let us say if the system is at Tsat and Psat, if you maintain the pressure higher than the Psat at same temperature, the liquid phase will consist of only liquid phase. When the system is at Tsat and Psat, if you reduce the pressure at the same Tsat, the only vapor will exist in the system. And when the system is at Tsat and Psat, if you try to increase the temperature at same pressure, only vapor will going to exist. When the system is at same Tsat and Psat, if you lower the temperature, what happens at same pressure? What happens? Only liquid phases exist. That is what this common sense thing we can discuss about. So because in future you are going to find out the volumes of the liquid and volume of the vapor in the system. Okay, first of all you should know whether you are dealing with the liquid or dealing with the vapor. So to get some idea of what the things, because you cannot see what is there in the system, we cannot keep the microscope or so inside this particular system, but based on some common sense judgment you can able to identify first what this substance is present in which kind of phase. Using this kind of chart, or table, you can able to justify that if you maintain if you change the pressures or change the temperatures and what kind of phase that can present in the system. So we will going to do some few examples, okay, later. Before that, observe this particular line, okay. First of all, you should know some information about this particular line, because this is the demarcation line from liquid to vapor and vapor to liquid transitions. So let us concentrate on this particular line. There are many equations proposed to track this saturation pressures and temperature, because this is the basis. Because first of all you need to identify saturation temperatures and saturation pressures. We have to look into this particular equations as many scientists proposed, so thereby you get an idea to calculate this kind of pressures and temperatures. So there are equations that come up based on this particular line. So let us deal with this line. So forget about the other lines. So we are dealing with the vaporization curve, whether a liquid to vapor transition and vapor to liquid transitions. So identification of saturation pressures and temperatures. That is, I told you, right? Pressure and temperature data. We are concentrating on this particular line. On this particular side is a liquid, and this particular it is vapor. So at certain temperatures and pressures, so all the points on this line are saturation pressures and temperatures. If you know the temperature, you can calculate the pressure. If you know the pressure, you can calculate the temperature. So what are the equations proposed to track this line? So the first one came up with a Clapeyron equation. Clapeyron said that Clapeyron found that slope of this particular equation. That means how my pressure is going to change with respect to temperature, that is nothing dP sat by dt. So if you wanted to find out this particular slope of this line, then you need to have the following information. Only enthalpy, phase change of enthalpy change during the phase change. L represent the liquid, V represent the vapor. So when a substance is changing its phase, then the enthalpy of change, enthalpy requirement because of this phase change is delta H LV divided by T and divided by delta V LV. Delta V is, gas volume is higher than the liquid volumes. So delta V is representing the change of volumes, that is vapor volume minus liquid volume. That is what delta V L into V. So that is what delta V is equal to vapor volume minus liquid volumes. So delta is latent heat of vaporization. So people, the closest come up with the more simplified expressions that they have taken. Here they have taken assumption that Delta V, you know what is the delta V? Change of volume of vapor volume minus liquid volume. Okay, molar volume of the vapor minus molar volume of the liquid. So compared to the vapor volumes, liquid volumes are less. Okay, because you can say vapor, the gas or vapor will occupy more volume compared to the liquids. That is, molar volume of the vapor is very much higher than the molar volume of the liquid. So in such cases, delta VLV is nothing but vapor volume minus liquid volume, which is equal to the vapor volume. Okay, that means liquid volume is negligible, so you can remove this particular term. Finally, delta VLV is nothing but vapor V into V. Okay, vapor volume. So if you in this equation, if you substitute the equation number 2, you get dp sat by dt is equal to delta HLV by T into V power V. Okay, this is the Clausius-Clapeyron equation. This is called Clapeyron equation. So based on this Clapeyron equations and Clausius-Clapeyron equations, many people came up with the finding out the line equations. You can see this is called the connecting the saturation pressures and saturation temperatures line. So many empirical equation proposed based on the concept given by Clapeyron and Clausius-Clapeyron and the things empirical relations such as Antoine equation, Wagner equations. These are the people that has predicted what is this particular line. So I can able to, but that means what this line talks about, that means if you know the pressure, you know the temperature. If you know the temperature, you know the pressure. So both the things can be calculated, the line equations. So this is the equation proposed by Antoine. Ln P sat is equal to A minus B by T plus C. Pressure in kilopascal, temperature in Kelvin. Okay. And using the above equation, we can able to find the saturation pressures and saturation temperature. Therefore, if you rearrange this equation, if you want to know the saturation temperature by knowing the pressure, you can you can rearrange this equation. Though temperature is nothing but B by A minus, this both equations are equally calculated. Simple, that's the same thing. So temperature is equal to B by A minus ln P minus C. A, B, C are called specific constants because this A, B, C depends what kind of molecule substance is present in the chamber. Okay, A, B, C is the specific to the component. Okay, and it is already listed in appendix B2 in the Smith Vaness Abbott book. If you look into the tables given the appendix B2, you can able to find out A, B, C of the Antoine constants are given. That means if you want depending upon the substance, you can able to find out what is the saturation pressure and saturation temperatures of that particular substance. For example, a small example, let us find saturation pressures given for N-hexane and 30 degrees centigrade. A, B, C are provided. If you substitute the values of A, B, C in the Antoine equations, by knowing the temperature is 30 degrees centigrade, that means you have to you have to change it to Kelvin before you put into this equation. So P sat is 24.98. That means in this particular chamber, if you can able to maintain this 30 degrees centigrade and 24.98 kilopascal, that means this particular N-hexane at these conditions will be at a saturated state. That means this is how you can able to find out what is the saturation temperatures and saturation pressures of a particular substance. Let us do the more analysis. I have already calculated. Let us see the effect of pressure and effect of temperature. Because if you look into this equations, I'm sorry, I'll come back. So this is N-hexane. The N-hexane normally in at saturation temperatures and saturation pressures, there is a possibility that N-hexane can exist in the liquid as well as a vapor. Okay, let us mark those things. So at 24.98 kilopascal pressure and temperature equal to 30 degrees centigrade, it is at a saturated conditions. What happens if you increase the pressure at the same temperatures? So I'm maintaining the temperature as a constant at 30 degrees centigrade. I'm slowly increasing the pressure. So as we have discussed in this session, that if you increase the pressure higher than the saturation pressure at the same temperature, this N-hexane will completely bring down to the liquid state. Okay, this is a subcooled liquid state. And similarly, if you reduce the pressure lower than the saturation, that means if you try to reduce the pressure by lifting the piston up, so now the pressure will be reduced at the same temperature. Now every molecule of N-hexane will become a vapor state. So that is what it is given. If pressure is greater than the saturation pressure at a T, it will form a liquid, that is T sat, and pressure is less than the saturation pressure at this temperature, then it will become a vapor. So similarly, let us see the effect of temperature now. Now let us keep the pressure at 24.98 kilopascal and change the temperature. So earlier it is a these are the saturation conditions. Saturation conditions are temperature at 30 and pressure is 24. So I am keeping the pressure constant. I am raising the temperature now. Now I am increasing the temperature greater than the saturation temperature. That means all the molecules of N-hexane will become a vapor because temperature is higher than the saturation temperature at this particular pressure. Now if we lower down the temperature, okay, it's a vice versa kind of thing, okay. If the temperature, if I lower down, I mean kind of if temperature is lower than the T saturated temperature, what happens? The entire N-hexane will become a liquid state. This is what the effect of pressure and effect of temperatures. Now the saturation data is very much important to identify the particular phase. Let us follow some more examples, okay. Identify a phase of compound N-hexane at different temperatures and pressures. For example, the data is given. Let us solve the different examples. The temperature conditions and pressure conditions are given. Okay. Let us assume the temperature in a container. The temperature is 0 degrees centigrade and pressure is 10 kilopascal. So based on this, we have to identify saturation. The temperature, based on the base of the temperature, I am going to solve this particular example. So our job is to identify at these conditions what kind of phase that can exist of our N-hexane. So to do that, I need to have the T-sat, P-sat data. So I know if you know the temperature, I can able to calculate the P-sat using Antoine equations. Okay, that at temperature is 0 degrees centigrade, saturation pressure is 6. But the system is at what pressure? At 0 degrees centigrade and pressure is 10 kilopascal. That means actual pressure in the container is higher than the saturation pressure. That means it will be in the liquid phase. So this is how we can able to identify. Similarly, this also at 60 degrees centigrade and 80 kilopascal and identify the phase of N-hexane in this chamber. So at temperature 60, I need to calculate the P-sat. Now again, the existing pressure compared to P-sat is higher. That means the things will be in the liquid state. Similarly, example 3 talks about the same thing at 90 degrees centigrade also. And saturation pressure is 189 kilopascal, but the pressure in the chamber is 195 at 90 degrees centigrade. That means there is a possibility that the entire the container consisting of N-hexane is in the liquid phase. So if you talk about the other things, at temperature is 0 degrees centigrade, pressure is 5 kilopascal in this chamber. So identify the phase. So at temperature T is equal to 0, the pressure is 6. Now but the pressure in the container is lower than the saturation pressure at this temperature 0 degrees centigrade. That means this N-hexane in this chamber will be the vapor phase. Similarly, these other two will follow the kind of phases we are talking about. Now let us talk about here the basis is that means with respect to, and in this example we have changed based on the pressure we have decided, and in the subsequent example based on temperature we are going to identify a particular phase. Example, there is a chamber consisting of temperature 5 N-hexane with temperature 5 degrees centigrade and pressure is 10 kilopascal. Let us take the basis of pressure. If at 10 kilopascal pressure, what is the temperature? Saturation temperature is 9.78 degrees centigrade. But the existing temperature is in the container is 5, which is less than the saturation temperature. That means if the temperature is less than the saturation temperature, then at this particular pressure, that means there is a chance that entire chamber consisting of N-hexane in the liquid phase. Similarly, at temperature equal to 50 and pressure equal to 90 kilopascal. So at pressure equal to 90 kilopascal, I have calculated the saturation temperatures. So saturation temperature value is 64.97 degrees centigrade. But you can see in the chamber the temperature is 50, okay, which is lower than the saturation temperature. That means there is a possibility that inside it will be an N-hexane in the liquid phase. So similarly, the example number 9. So let us talk about the vapor phase. So temperature is 15 degrees centigrade and pressure is equal to 10 kilopascal in this chamber. So at pressure equal to 10 kilopascal, I calculated using Antoine equation. Saturation temperature is 9.78. Now you can compare with this. Now the existing temperature in the chamber is higher than the saturation temperature. That means the possibility in the chamber is N-hexane is in the vapor phase. Similarly, the other two examples follow. Okay, so identification, because we are moving into the example, finally all the concepts behind is we are driving towards estimations of molar volumes of liquids as well as molar volumes of vapor. So this kind of, because before we go into the actual topic, you should get an idea of whether you are dealing with the liquids or vapors. So in this particular lecture, now you got an idea that in this present conditions, what is the possibility, whether it's a liquid or it's a vapor. So based on that, you can get an idea where to start, whether you have to find out the liquid volumes or you have to find out the vapor volumes. I hope now you get a base idea then what is the use of saturation pressures and saturation temperatures. And thank you. Let us meet with the new lectures.